Good morning, good afternoon. Welcome to the first lesson in Unit 2. So we're going to start off with a couple of days talking about relations and functions. I think that vocab is vocabulary you've heard before, but it's not always well understood. So we're going to start off by defining in math what a relation is. Okay, I had to do a do-over on writing that. A relation. In math, a relation is any set of ordered pairs. And just so we're sure of what we mean by a set of ordered pairs, an ordered pair is the XY. It's called a pair because there are two of them, and it's called ordered because the X always comes first. So it does matter which number you put first. The input is your X and your output is your Y. And that's kind of an important concept there. So it's any set of ordered pairs. There doesn't necessarily have to be a pattern to the ordered pairs, although usually in math there is a pattern to it because that's really what we study. There are 4 ways that you can display a relation. So 4 ways to display. I think 3 of these you're very familiar with, and the 4th one is going to be new. So the first way that you can display a relation is simply by listing the ordered pairs. So I've got a set of ordered pairs here that we're going to use for all of our examples. We have -3, 4, 3, -1, 4, -1, and 4, 3. And just to remind you, the first number is the X, the second number is the Y. You have your input and your output, and you do have to write your ordered pairs this way. So you have to use parentheses. You cannot use brackets, either the square ones or the squiggly ones. You cannot just do 2 numbers separated by a comma. It has to be 2 numbers separated by a comma inside the parentheses. That's really a non-negotiable when it comes to listing your ordered pairs. The second way that you are familiar with is writing them in a table, and the table is really almost just like listing the ordered pairs, except instead of implying the X and the Y by their position within the ordered pairs, you would head up 2 columns like so. And I don't know if you can hear the cat. There's a cat who really wants to be a part of this math lesson, and he's not going to be a part of this math lesson, but he wants to be, if you can hear him. So the table, so we have the list of ordered pairs, we have the table. The third way that you are familiar with is by graphing them. And what I really would like to do in this particular unit is solidify the relationship between like the table and the graph, and then in a little bit we'll talk about the equation, because they're all different ways of representing the same relationship. And there are advantages and disadvantages to each way of representing them. So what we choose really depends on what we're trying to do. With the graph, do remember that this right here is not a graph. This is what we would call the coordinate plane. The graph is what we put on the coordinate plane. So it's the points, the line, the parabola. This right here is called the coordinate plane. Now, to be honest, we do get lazy about how we say that, and you'll hear teachers call this right here a graph. You might even hear me do it. If I do it, I'm being lazy. The horizontal axis is your X, the vertical axis is your Y. On your horizontal, your positive numbers go to the right and your negative numbers go to the left. It's a regular garden variety number line, just like we were doing in the last unit. And your Y-axis is also a number line, except it's going vertically. Your positive numbers go up and your negative numbers go down. Usually that's not an issue, but every year I do have some students that will switch the X and the Y, and we'll also like switch up the number line so like the positive and negative numbers go in different directions. So if I want to plot the point -3, 4, the -3 goes with the x coordinate, so I'd count left 3 and then +4 up. 2, 3, 1, 2, 3, 4, which I think is thereabouts. If I had, there's a graph paper option on this program, I just didn't activate it. The point 3, -1, I'd go right 3 and down 1. So right about there. Then we have 4, -1, so I would go right 4 and down 1. And then 4, 3, so right 4 up 3. And there's no real pattern to where those points are, which in itself could be useful information. Now, the fourth way to represent your relations is with something called a map. And this might be new. Now, to do the map, you create like 2 ovals, and one of them is your input, okay, and one of them is your output. So we have our input in one oval and our output in the other. And then you list all the numbers that can be used as an input. So we go down our list and we have -3, 3, 4. But notice that I don't list the 4 again. So I'm pointing over here to the right, left, if you can't see where my little arrow is. I have the number 4. Once the number 4 is in that set, I don't repeat it. So you should never have the same number in the circle twice, or more than once. So once 4 is in the set, 4 is in the set. And then we do the same thing with our outputs. So I have 4, -1, and 3. And sometimes students will say, well, wait a minute, you already had the 4, you already had the 3, you shouldn't rewrite them. What you don't want to do is duplicate them within the set. So I don't want to have more than one -1 in the output set, but it's okay to have like a 3 in each of them. And then what we do is we simply draw arrows showing how an input maps to an output. So -3 maps to 4. You just draw a little arrow. 3 maps to -1. 4 also maps to -1, and 4 maps to 3. And then again, you don't duplicate the values in the map. So don't duplicate the numbers. Or I guess variables if we had variables. So don't duplicate the numbers. So those are the 4 ways that you can express a relation. Now, other vocab that you are probably familiar with. I didn't actually learn this vocab until Algebra 2, but I do know that they introduced this vocab in Algebra 1 now. The domain is all possible inputs. It's all of the possible x values. So what could you plug in or use for your x values? Okay, so you want to associate domain is with x. And figuring out the domain, when we first begin dealing with domain, we would say the domain is all real numbers, which we talked about in like our very first lesson. Like, what are the real numbers? It's everything on the number line. If you can find it on the number line, it's a real number. And then as we study more types of relations and functions, we will start to exclude stuff. So it's actually easier to think of the domain as everything or everything but, like everything but a 3. The range is all your possible outputs. And I am putting that in parentheses because, outputs. Because once we start dealing with equations, we don't have a list of the inputs and outputs. And that would be your y values. There's actually some other vocab with there. There's with that, it's like stuff like called the codomain, and like you wouldn't hear about that until college. So for you guys, think domain are all the possible x values, range are all the possible y values. What are all the things you could put in or get out? So if we were asked to state the domain and range for the relation on this page. So let's go and I need a new color. We'll use brown. If you were asked to state the domain, okay, so state, domain, and range. Here is what I would want you to do. So we're looking down, if you're following along, I'm in like the lower left-hand side there. If you were asked to state the domain and the range, you would do this. You'd put like a D for domain and then a colon. Then you would open up your squiggly brackets and you would list all the different numbers that you have for x. So in this case, it would be -3, 3, and 4, and then you would close your squiggly brackets. Do not list the 4 twice once it's in the set. So the domain for this relation would be -3, 3, and 4. The order actually does not matter, but for sanity's sake, I usually like students to put them in numerical order. It just makes things easier to grade. For your range, you would write a capital R and then a colon, and then again open up the squiggly set brackets, and then we have 4, -1, and 3. And if you want to be nice to Miss Taylor, you would write -1, 3, 4. You'd put them in numerical order, but I want to be really clear, that's the same set. So when you're dealing with sets, the order does not matter. My dual enrollment class right now, they're getting ready for a test like all on sets. So order does not actually matter. It's just nice if we put them in numerical order. So that brings us to functions. We are all about putting the fun in function today. So what are functions? Functions are specific types of relations, and they're really important. We will spend just about all of Algebra 2 studying different types of functions. And then for those of you that go to pre-cal, you will study more functions. You'll study your trigonometric functions. Not every relation is a function, and not everything you study in math class are functions, but they are really important. And so the definition of a function, it is a relation where each, I think my hand was on the bottom of my screen here, where each x maps to only one y. And then if you're following along at home, if you're watching this after the fact or you're rewatching this, this is a good place to just stop and pause and really like consider that definition. Every x value only matches to one y value, and it's super easy to get those flip-flopped. So on the next slide, I'm going to have 4 examples, and then what we'll do in class is I'll pause, I'll give you guys a chance to look at them and decide whether or not they're functions, and then we'll talk about the answers to that. Okay, check these out. We have 4 different problems there. So the question is, looking at this map, is this the map of a function? Is the green one a map of a function? Is the yellow gold thing a map of a function or a function? And is the table here, does that represent a function? So we'll pause and discuss together in class, or I will do the explanation in the video and we'll fast forward through it in class. I don't know how this is going to work when I do this in the middle, but take a moment and look at them. Okay, with this first one, we'll actually look at these two together. One of these is a function and one of them isn't. And it's very easy to get them flip-flopped. So remember, the definition of a function is where each x maps to only one y. So what you want to do to determine if it's a function is you're going to look at each x and see if each x only goes to one y. So I have the 1 only goes to a 2. The 2 only goes to the 4, and the 3 only goes to the 2. Now, some students will look at that with the y, and they will say, but wait a minute, 2 different numbers are going to the 2, that means it's not a function. That's totally okay. There's nothing in the definition of function that says you can't have 2 different x's going to the same y. What it's saying is you can't have the same x go to 2 different y's. So this one is actually yes. This one, though, where I have the 1 only goes to the 3, but the 2 actually maps to 2 different y's. Remember the definition. X maps to only one y, and if you look at this x, it's mapping to 2 different y's. Now, I do have a little analogy that you can use to keep these straight. I want you to think of the x's as being people and the y's as being places. So we have like people and we have places. When the bell rings, is it possible for 2 of you that are sitting in this class, your people, to go to the same place? Whether this is a face-to-face class and you might go to the cafeteria, or you might go to your 3rd block class. Would that be okay? That would be, or 3rd block. I don't know why I picked 3rd block. Your next block class. But that would be totally possible to do. But would it be possible for one person to go to 2 different places after leaving this class? No. So if you think of like people and places, that might help you keep that straight. Now the next one, remember you're looking for x's that map to only one y. So 0 maps to 1, 1 maps to 2, 0 maps to 3, and that's going to disqualify it because the 0 maps to both a 1 and a 3. So 0 goes to 1 and to 3. And then our last one, -3 maps to 4, 3 maps to -1, 4 maps to -1. That's okay. Okay, it's totally okay to have the duplicating y's. 4 maps to 3, and that's going to disqualify it. So 4 goes to -1 and to -3. What some students will do is they'll just simply interpret this as looking to see if the x's duplicate. And that, I mean, that does work just to see if the x's duplicate, but it's important to know why. That's the thing that disqualifies them. So remember, go back to the definition. In a function, it's a relation where each x maps to only one y. So let's talk about the vertical line test. And really, I want to reason through this so that the vertical line test isn't just something that you do, it's something that you understand. In all of these, you'll notice like how we're showing the relations. We're showing the map, the list of ordered pairs, the table. We are using, try to click back. We used these 3, the list, the table, and the map. If we're going to depict our relation as a graph, we actually have another tool we can use to figure out if it is a function. So think about this. If you had a collection of ordered pairs and you had the point, we'll say 1, 2, and 1, 3, we know that this would not be a function because I have the same x going to 2 different y's. When I graph that, the way it looks is it would be the point 1, 2 and the point 1, 3. And notice that they graph as points that are stacked vertically. So you have a word there that you can't read. Points stacked vertically. That means like one right above each other. So if you have something that is not a function, you can spot that by doing what's called the vertical line test, where you would look to see if at any point on the graph you had 2 points that were stacked over each other. If you do, we talk about that as we fail the vertical line test and we know that something is not a function. And there's our little summary of it. So to summarize, when one x maps to more than one y, the points will be directly over each other. This is the example from the notes for those of you following along with the notes. I don't know why I picked an 8. Like, why would I do that? But this is similar to the one I just did. So we have to go 1, 2, 3, 4, 5, 6, 7, 8. 1, 2. And the points will stack over each other. So the vertical line test is much, much easier to demonstrate than it is to actually explain. But on the next slide, I'll write out what the vertical line test is, and then we'll look at 3 examples of using it. So here's the vertical line test written out. I'm not particularly interested in you writing out this vertical line test and having it written out, because again, it's so much easier to just show you what we mean by it, and as long as you know how to use it, I don't really care if you have it written out. But for the sake of it, here's what it is. If a vertical line passes through more than one point on the graph at once, okay, not like in the action of sliding, then the graph is not a function. And usually the way we'll talk about this is like a graph either passes the vertical line test or it fails the vertical line test. And if it fails the vertical line test, where does it fail it? And if that's the case, then you're looking for the location where the 2 points are stacked over each other. So I've got 3 graphs in the notes, and we'll finish this part up, and then we'll call it a day for the first lesson in Unit 2. So we have 3 graphs here. I think you should all be familiar with the graph on the left. That is a line. The one in the middle looks like it could be a parabola. We don't have a whole lot of information about it. And then the one on the right looks like it could be like a sideways parabola. So take a moment, decide whether or not these are functions. It's like a simple yes, no. If we're doing this in class, then this will be the end of the video and we'll talk about them and go over the answers together. If you're watching this on your own or making up the lesson afterwards, then I will explain it next. Okay, so this first one is a function. So this first one we would answer yes. And the way we would reason that is if I slide a vertical line across this whole graph, it will only ever cross the graph once. So to kind of illustrate that, if my vertical line is like right here, it's crossing my graph there, but it's only crossing once. If my vertical line is over here, then it's crossing, but again, only crossing once. And that's, we don't ever have 2 points stacked up over each other. The next one is also a yes. And if I draw my vertical lines, like I do have the vertical line crossing the graph, but it only ever crosses it once at a time. And this last one is a no. And if you were asked why, you could say the way you would express that is it fails the vertical line test. So if I were to look at the coordinates of these 2 points here, they would have the same x coordinate, but they would have 2 different y coordinates, and that of course is why it fails. A graph only has to fail the vertical line test at one point in order to not be a function. So it could be a function everywhere, and then if at just one location it fails, then it would not be a function. So let's look at this just for fun. If I have a line and then I have like an additional point, that is not a function because right here I would have my 2 points stacked. I'd have a point there and a point underneath it. And so it only has to fail it once to not be a function. And that's a wrap on relations and functions part 1.